Hello world, it's Siraj, and imagine that you've built a game and you want to predict whether or not your players are going to continue playing next month or not. You want to classify your players as going to churn or not going to churn. And you've got a single data point, and that is the amount of money that that user has spent in the game this month, either withdrawn or deposited to buy some in-game currency or digital gold or some kind of items, right? And based on that data point alone, you want to predict whether or not the user is going to continue playing the game or not. Now, normally when predicting customer churn, as it's called, you'd want to use several data points. You'd want to use the time that the user has logged in. You'd want to use a bunch of different features. But for this simple one-dimensional example, we're just going to use that because what matters is the model that we're going to learn today. And the model is a Gaussian Mixture Model. That's what the model is called, and it is a universally used model for generative unsupervised learning or clustering, which is what we're going to do. It's also called EM clustering or expectation maximization clustering based on the optimization strategy that we're going to use, which we'll talk about. But the idea is very simple. For a given data set, and in our case it's going to be the amount of money withdrawn or deposited, each point is generated by linearly combining multiple Gaussians. Okay, so that's what we're gonna do. And before we start with this amazing example and code, I wanna say one thing, okay? This is a message from Siraj. This is the message. The message is, this is a 30-second message. I went and I met subscribers for this channel. I met the community. Here in Amsterdam, I met 15 or so people. I went to London this past weekend and I met about 15 or so people. And I was just blown away by the quality of people that have subscribed to this channel. The community that we have built is incredible. Seriously, there are people working for the United Nations. There are people who I have met who are working to create a machine learning community in Tunisia. There are people who have apps with 500,000 plus users that are trying to stop smoking. There are people who are working on global warming. They are legitimately working on using machine learning to prevent global warming. And it is so inspiring and it is amazing. It inspires me and it increases my conviction to help you guys get better because it's not about me. You guys are the real inspiration. You are my hero, okay? You are my hero for watching this, for giving your attention to machine learning. We are the most important community in the world because we have an interest in the most important technology in the world. We are the most important community in the world, and we are the ones who are going to solve the problems in this world using machine learning in the way that only we can. Remember, we are smart and we are cool. I have met you guys, and I'm going to continue meeting you guys in person. I'm going to India next month. I am very excited for that, and I'm just gonna meet all you guys everywhere. I'm gonna do a world tour at some point, but anyway, it's a very exciting time to be in this field, and we are the real change makers, okay? We are the ones who are going to solve these problems. So it's amazing that we exist, and we are growing at a rate of 500 to 800 subscribers a day. Reply to people in the comments. Ask people for questions in the Slack channel. We are growing. Startups have been built in the Slack channel, by the way. It is incredible what is happening. It is truly incredible. Anyway, I was just excited about my past weekend in London, meeting you guys, and I'm gonna continue to do so. Back to this. So we're gonna build a Gaussian mixture model. And first of all, what is a Gaussian? Now, I know I've kind of talked about this before, but let's go into it a little bit more. A Gaussian is a type of distribution. It's a very popular and mathematically convenient type of distribution. But a distribution is a listing of outcomes of an experiment and the probability associated with each outcome. So let's say we've got some kind of game, right? And you could get a score of 1, a 2, a 3, 4, 5, 6. You could get a set of scores, and then you want to calculate the frequency or the amount of times that a person has made this score, right? So the tally and the frequency columns are the same thing. And so what you could do is you can notice that there is a peak here, that the number 9, right? So notice how this kind of follows a bell curve. The frequency goes up and then it goes down. Now, it's not exact because 7 is greater than 6, but more or less it looks like it follows a kind of bell curve. The frequencies go up as the scores go up, and then it has a peak value, and then it goes down again. And we can represent this using a bell curve, otherwise known as a Gaussian distribution. And a Gaussian distribution is a type of distribution where half the data falls on the left of it and the other half falls on the right of it. So it's an even distribution. And you can notice just by the thought of it intuitively, that is very mathematically convenient. Right? And so what do we need to define a Gaussian or normal distribution? Well, we need two variables. We need a mean, which is the average of all the data points, and that's going to define the center of the curve. And then we need the standard deviation, which describes how spread out the data is as well. And once we have that, we can write out this curve. And this is used throughout many fields, and you can think about many examples of where anytime you have some kind of data that's increasing, has a peak and decreases, very likely a Gaussian distribution would be a great distribution to model this data. Whether it's a car or a roller coaster that's increasing in velocity, reaches a peak and then decreases, or a sound wave, acoustic waveforms, there's a lot of applications of this. Now, so that's a Gaussian distribution, and I'll show you the formula in a second. But this is these are multiple Gaussian distributions, right? Where we have multiple means and multiple standard deviations. And if we have those, we can plot out multiple Gaussians, which is what we're going to do in a second. But the formula for a Gaussian distribution using the mean and the standard deviation, once we calculate those two things, we can write out this formula, this graph. And this is the formula for it, and it's called the probability density function. That's what it's called. So we can say for a given point x, we can compute the associated y, which are all of those values. Remember, in a one-dimensional case, we know all the x values. We want to compute the y values, and the y values are the probabilities for those x values. So then, given some new x value, we can output the probability of that x value being a part of the curve, or being a part of the data set, or being a part of the class in this case. So we can say 1 over the standard deviation times the square root of 2 times pi times the natural number e to the negative x value, which is the data point, minus the mean squared over 2 times the standard deviation squared. So this is a function of a continuous random variable whose integral across an interval gives the probability that the value of the variable lies within the same interval. So we have some interval. So that's a Gaussian distribution, and that's the formula for one. So what is a Gaussian mixture model? Well, sometimes our data has multiple distributions, or it has multiple peaks. It doesn't always just have one peak, and we can notice that. We can look at our data set and we can say, well, it looks like there are multiple peaks happening here. There are 2 peak points, and the data seems to be going up and down twice, or maybe 3 times or 4 times. But if we think that there are multiple distributions, Gaussian distributions, that can represent this data, then we can build what's called a Gaussian mixture model. And what this is, it is a probability distribution. It's more a probability, you can think of it as just a probability distribution that consists of multiple probability distributions, and that are multiple Gaussians. So for d dimensions, where d is the number of features in our data set, the Gaussian distribution of a vector x, where x equals the number of data points that we have, is defined by the following equation. And so you can see how you can substitute d for the number of features we have. This is for the mean, and so sigma represents the covariance matrix of the Gaussian. And so you notice how we're not using the standard deviation. Instead, we're using the covariance matrix when it comes to the Gaussian mixture model. And this is what it would look like, right? So in the case of 2 dimensions, it would look like this. It would give us a curve for all of our possible data points. And so why do we use the covariance? Well, the covariance is a measure of how changes in one variable are associated with changes in a second variable, right? They co-vary. It's not just about independence of variation. 2 variables and how they change depend on each other. They co-vary. And the covariance, well, to be technical, it's called the variance-covariance matrix, is a measure of how these variables relate to each other. And in that way, it's very similar to the standard deviation, except when we have more dimensions, the covariance matrix, as opposed to the standard deviation, when we plug it in here, gives us a better, more accurate result. And so The way we compute the covariance matrix, I've talked about this before when we talked about eigenvectors and eigenvalue pairs, but the parameters that it uses are the number of scores in each of the data sets, the variance, the covariance, and where C is the size of the number of columns in the data, right? It's a column by column matrix. I will compute this in a second. But the probability given in a mixture of k Gaussians, where k is the number of distributions that we believe that there are. In our case, we believe that there are going to be 2. Okay, let's just say we think in our data set there are going to be 2. So for k Gaussians, 2 in our case, we're going to multiply W, which is the prior probability of the jth Gaussian, times the value that we just looked at up here, right here, where this is the Gaussian distribution of the vector of our data points. And so once we have this value, then we can say we can multiply it by W, where for each of our Gaussians, and that is going to give us our probability value x for a given x data point. And so this is what it looks like, right? So if we were to plot multiple Gaussian distributions, it would be multiple bell curves. But what we really want is a single continuous curve that consists of multiple bell curves. And so once we have that huge continuous curve, then given our data point, it can tell us the probability that it's going to belong to a specific class. Okay, and so what class? How do you tell what class something is given this curve? Well, let me go to the bottom here. Once we have that best fit mixture, notice this image right here, we can tell what class it's in by where it falls on the curve for the one-dimensional case. So this would be class 1, this would be class 2, this would be class 3, like that. Now in the two-dimensional case or three-dimensional case, it's easier because they are circles, right? Like k-means clustering, right? They're circles. And that's what they come out to if we were to measure probability values just like this for not just one feature like we're doing for us, but multiple features, like 2 features. So if you have probability values for the y-axis, which is a second feature set, like maybe the number of other users that this person has friended, and then this is the probability of the amount that the user has either deposited or withdrawn, then we can draw these cluster circles. But for the one-dimensional case, it looks like that bell curve. And so the problem that we're trying to solve here with the GMM is given a set of data points, x, let's draw from an unknown distribution, which we're going to assume intuitively is a Gaussian mixture model. That is that the data set consists of multiple Gaussians. Estimate the parameters theta, which consists of the mean and other values that we'll talk about, of the GMM model that fits that data. And the solution, the way we find these parameters of our model, which is what machine learning is all about, mathematical optimization, is by maximizing the likelihood P of x, the probability of x, given our parameters, and x is the data point that we want to predict the probability, the class, we want to maximize the likelihood that x belongs to a particular class. We want to find, the way we do that is to compute the maximum likelihood estimate, which is this equation right here. We want to find the maximum probability value for a given class. That is, we want to find the class that this data point x is the most likely to be a part of. And so notice how, I also added this image to show how, given in the two-dimensional case, these distribution bell curves come out to circles if you have distributions for not just one axis or one dimension, but 2 dimensions. So it's very similar to k-means. Now we've talked about the k-means algorithm. It uses the same optimization strategy, which is the expectation maximization algorithm. It's similar to k-means in that k-means finds k to minimize x minus the mean squared. But the Gaussian mixture model finds k to minimize x minus the mean squared over the standard deviation, over. And the reason that we add the standard deviation into the mix is because the denominator, the standard deviation squared, takes variation into consideration, when it calculates its measurement. What does this mean? This means that the k-means algorithm gives you a hard assignment. It either says this is going to be this data point is a part of this class, or it's a part of this class. Now this is great in a lot of cases. We just want that hard assignment. But in a lot of cases, it's better to have a soft assignment. Instead, we want the maximum probability. Okay, this is going to be 70% likely that it's part of this class, class A, but we also want the probability that it's going to be a part of other classes, right? It's not just a single output. It's not a discrete output. Instead, it is a continuous output. It is a list of probability values, right? It could be a part of multiple distributions. It could be in the middle. It could be 60% likely this class, but 40% likely this class, not just class A. And so that's why we incorporate the standard deviation. So how is this thing optimized? Well, it's optimized using the expectation maximization algorithm. So the basic ideas of the EM algorithm are to introduce a hidden variable such that its knowledge would simplify the maximization of the likelihood. So we pick some random data points, right? We pick some random data points. We draw a distribution around that data point. We then estimate we then update our parameters using that generated distribution, and then we repeat the process, and every time we draw a new data point, it's going to be closer and closer to the data point that best fits the data set that we have, such that if we were to draw a distribution around that data point, it would fit that data set the best. And so there are two steps. There's the E step, the expectation step, and the expectation step is to estimate the distribution of the hidden variable given the data and the current value of the parameters. And then the M step, the maximization step, is to maximize the joint distribution of the data and the hidden variable. So that's the high level, and we're going to talk about the implementation details in the code. But you might be thinking, well, wait a second, what about gradient descent? You might be thinking about that because we've talked about gradient descent, and the entire industry loves gradient descent. And here's the thing, you can obtain the MLE using gradient descent, but what is the deal with gradient descent? Gradient descent is using the derivative. You are computing the derivative of a node, right? A node in some kind of graphical model. You're computing the derivative, and what the derivative tells you is the direction. It tells you the direction that your data wants to move in. What direction should you move the parameters, theta, of your model such that the function, your model, is optimized to fit your data? But what if you can't compute a gradient? What if you can't compute a derivative? You can't compute a derivative of a random variable, right? This Gaussian mixture model has a random variable. It is a stochastic model. That is, it is non-deterministic. You can't compute the derivative of a random variable. That's why we're not using gradient descent in this case, because you can't compute the derivative of a random variable, okay? So there are actually ways to compute the derivative of a stochastic model, like a variational autoencoder, but it's a trick. And if you want to know more about that, I've got a great video on that. Search variational autoencoders Siraj on YouTube. It'll be the first link. So back to this. So when should you use this thing, right? When is this actually useful besides customer churn? Anomaly detection. Think about any case where you are trying to cluster data, where you are trying to classify data that does not have labels. So one use case is trying to track an object in a video frame, right? If you know the moving object's distribution in the first frame, we can localize the object in the next frames by tracking its distribution. That is, you know kind of the probability distribution of all the possible ways that the subject can move, and based on that, you can create a bounding box around the subject such that in the next frame, it's very likely that that subject's movement will fit into the bounding box. I have some related repositories here for using TensorFlow and a Gaussian mixture model to classify song lyrics by genre. Very cool use case using TensorFlow. definitely check it out. It's called Word to Gaussian Mixture. Very cool. Check that out. It's got some great instructions, and I've got one more, which is a great general purpose tutorial for Gaussian mixture models. It's a Jupyter notebook. Definitely check that out as well. And I've got some great links for you in the description. All right. So check that out as well. Got the great graphs and everything. So let's look at this code. Okay. So in this code, we're going to import our dependencies and then test out a distribution graph. Let's just see if we can draw out a distribution orthogonal or unrelated to our data set, just to see if we can do that. So we're going to import 4 dependencies here. The first one is matplotlib, which is our handy dandy plotting tool. And the next one is NumPy, which we always use for matrix math. Then we've got SciPy, which is going to help us normalize our data and compute the probability density function, which we talked about earlier, right? I showed you the equation for that. And then we have one more, Seaborn, which is also going to help us plot, specifically colors. Okay, so once we have our 4 dependencies, we can go ahead and start this. So the first step is for us to plot out a Gaussian distribution. Let's just see if we can do that first. So we've got, let's just say we're going to use NumPy's linspace function to return an evenly spaced set of numbers over a specified interval, which is -10 to 10. We have 1,000 of these data points that we want to generate and then look at. We have our real data set in a second, but this is just for the sake of an example. And so then we want to create a normal continuous random variable, and that's what the stats.norm.pdf, the probability distribution function is going to help us do. And so we say LOC equals 0, and this specifies the mean, so a mean of 0, and scale is 1.5, and that's the standard deviation. So we're going to draw a Gaussian distribution using those 2 parameters. We're going to plug those into the probability density function, and it's going to output the y values for all of our x values, right? We gave it our x values. It's going to plot out all of our y values. So then to plot it out, all we have to do is use matplotlib to plot out all of our x values and all of our computed y values, and then there it is. So we can write out a Gaussian distribution easily. We can do that, okay? So let's go into our data set. We're also going to import pandas, and we're going to read our data set here. It's a CSV file, and we can read it into a pandas data frame object, which is very easy to manipulate in memory once we have it there. And we want to show the first 5 examples. And here we are. We have the first 5 examples, okay? So for each of these are users. Each of these are different players, and the amount that that player has spent in a given month, this month, in Bitcoin, okay? In Bitcoin. So, or it's normalized, any currency it doesn't really matter what currency it's in, but it's in Bitcoin, okay? And so it's either a positive number, it's a negative number, that means that the user withdrew that amount, but the idea is that that's it. We've got one feature. So it's a one-dimensional problem, and we're going to write out a probability distribution for that single feature. And if we do that, then we're going to be able to predict the class of a given user based on how much this user has either spent or withdrawn, whether or not they're going to churn or not. Okay, so that's our data set, and now we're going to show the distribution of the data as a histogram. So let's show it as a histogram as well. So this is where Seaborn is going to come in. We're going to say Seaborn, create a distribution plot given our data that we've loaded into memory with pandas. We want 20 bins of this data, and let's plot it out. Let's see. Dist plot. Okay, so that's the distribution, that's the histogram of our data, right? So for all of those number of players, this is what it looks like. So we could look at this and we could say, oh, okay, so it looks like 1 Gaussian might fit this, but 2 looks better. Let's see. Let's try out 1 to see. Okay, so that's, I mean, clearly two distributions would be better than 1, right? You can see 2 peaks here. So 2 distributions would fit this data better than 1. So that's why we're going to use a Gaussian mixture model instead of a single Gaussian, right? So we want a continuous bell curve, a continuous curve that consists of 2 bell curves. So to define this model, two normal distributions are going to have 5 parameters. Four of them are the first four are the mean and the standard deviation for each of those distributions, 1 and 2, and the fifth one is the probability of choosing one of them. And so the way we're going to write out this Gaussian mixture model, where theta equals those four values and the probability of choosing one of them, W, is just like this. And this is the probability density function for a Gaussian mixture model consisting of two Gaussians. Now we looked at the probability density function for a single Gaussian and it looked like this right here. And this is what it looks like for two distributions, right? Right? We get it so far. So now we're going to fit this model. That's our model, right? All machine learning models are functions. They are functions where we initialize those parameters randomly or using some kind of, smart sampling method or something. But we initialize those parameters very stupidly and then we learn what the best or most optimal ones are. And in neural networks and a bunch of convex optimization problems, we generally use gradient descent because we can compute the derivative of deterministic nodes, but this is a stochastic model, so we're going to use the popular expectation maximization algorithm, which is a two-step process. We first perform E, which is to update our variables, and then M, which is to update the hypothesis. What do I mean? Well, this is an iterative method for finding the MLE that estimates the parameters in statistical models. So we start with some initial values, perform the expectation step, and then the maximization step, check if it's converged or not by some threshold that we define, and if it hasn't, continue iteratively, and if it has, stop. So the expectation step, given the current parameters of the model, estimate a probability distribution. Maximization step, given the current data, estimate the parameters to update the model, and repeat. So more formally, using the current estimates for the parameters, create a function for the expectation of the log likelihood. And then for maximization, compute the parameters maximizing the expected log likelihood found on the E step. So the M parameter estimates are used to determine the distributions of the latent variables in the next E step. So EM is trying to maximize the following function, which is what we define the probability density function up here, where X is a directly observed variable, that is our data point. Theta are all of those parameters, those 5 parameters of our model, and Z is not directly observed. That is the latent variable. That is the random value that we plot, right? To continue, and it gets more and more smart. It gets more and more optimal where we plot it as our model learns. Okay, and Z is a joint distribution on X. So it's a distribution between the latent variable that we've plotted and the Gaussian that we've already plotted. So there are 4 steps. If we think about it, there are 4 steps. We first initialize the parameters of our model, theta, and then we compute the best values for Z given theta, and then we use the computed values of Z to compute a better estimate for theta, and then repeat. So in another way to say this, and I'll show you a visual way in a second, but we want to initialize the parameters of the model either randomly or usually randomly, and then we find the posterior probabilities of the latent variable given the current parameter values. And then the M step is to re-estimate the parameter values given the current posterior probabilities. And we repeat that process again. So check this out. Visually, this is what it looks like. So we have 2 Gaussians. So in this case, we have probabilities for 2 features. So these are circles instead of those curves, right? Instead of those bell curves. And so we have 2 Gaussians and they're just randomly we generated them and we have our data points. So what we do is we say for each of those data points, which Gaussian generated it. So we give them all probabilities for each Gaussian. So that's the E step. For each point here, estimate the probability that each Gaussian generated it. In our case, we have 2 Gaussians, right? So we're going to estimate the probability that each data point is from the first A, and then the second B. Okay? And so when we have that, then we compute M. The M step is to modify the parameters according to the hidden variable to maximize the likelihood of the data and the hidden variable. And that's it. And so every time we do that, these Gaussian curves, these Gaussian distributions, these clusters are going to be more and more optimal to fit the data where they need to classify, to distinguish between classes. So back to our data. So let's define what a Gaussian looks like, right? So we'll give a Gaussian its own class. And so a Gaussian is initialized by the mean and the standard deviation. So we calculate that first from our data points, and we can do that very easily, right? For the mean, it's just add all the numbers up and then divide by the number of them. And for the standard deviation, it's the formula for that is look up there. That's the formula for it. Okay, so back to this. So once we have those, we can compute the probability density function that we looked at up there. The probability density function is this, right? So we can compute this programmatically, which I'm going to do right now. So programmatically, that looks like this, right? Just like that. Same thing. And so we can say, let's find the Gaussian of best fit for our data. So we have our data in a data frame, and let's find the Gaussian of best fit. And so these are our ideal means and our ideal standard deviations for our data. But that's not enough. We want two, right? It's not enough to just have one. That's too easy. There's no expectation maximization algorithm happening there. We don't really need it. But if we were to plot out this Gaussian, very easy. It's a single Gaussian, but it's not well fit to the data. We want two of them, right? So we're going to keep going here, and this is where the expectation maximization algorithm comes into play. So first, we randomly assign k cluster centers. In our case, k are the number of Gaussians, right? Not k means k where they are the number of Gaussians, 2. And then we iteratively refine these clusters, or bell curves, based on the 2 steps. For the expectation step, we assign each data point x to both clusters, the probability with the following probability. And then the maximization step is to create an estimation of the model parameters given those probabilities, and then repeat them such that the probabilities are maximized for each class. So then we'll create a class for our Gaussian mixture model. We've already created a class for our Gaussian, but here's for our Gaussian mixture model. So for a mixture model where there are 2 Gaussians, we don't just need one mean and one standard deviation. We need 4. In fact, we need 5 parameters, right? We need the mean and the standard deviation for one Gaussian. We need the mean and the standard deviation for the second Gaussian, and we need our data set as well as the mix, which is the initial W value. Remember the W value? And so we'll initialize both of them. So that's why we created that first Gaussian class, so we could easily initialize 2 Gaussians, just like that, using both means and standard deviations, as well as the W value, right, which is going to be updated over time, the weight value. And the weight defines how mixed these distributions are, how mixed both of them are. So now for the E step and the M step. So basically we make initial guesses for both the assignments of points to the distribution and their parameters, and then proceed iteratively. So once we've initialized the assignments and parameters, we can alternate between the expectation and the maximization steps until our estimates converge. That means that they do not change much between iterations for a mixture of Gaussians, and this is similar to convergence in k-means, right, which I've talked about, I think a few lessons ago. K-means clustering, Siraj, search that on YouTube. So for the E step, we first initialize the log likelihood as 0, which we're trying to maximize, and then we say for each of our data points, compute the unnormalized weight values using both of our data points, and these are the probability values, and then we compute the denominator by adding both of them together. We normalize them by dividing both of those weights by the denominator and add them both into the log likelihood. So we compute the log of the sum of both of those values, and that gives us the log likelihood, and we return the weight tuple. That are our parameters of our model, right? And so once we have that, we'll use those as parameters for the maximization step, right? That is, we want to optimize those weight values. So we'll compute denominators of our weights, right? So zip tells us the absolute values of our weights, so it's all positive, which just makes things a little more pretty mathematically for both of them. And then we'll take the sum of all of those values, both on the left and the right side, and we'll compute new means and new standard deviations for our new distributions, right? We're updating them every time. We're maximizing the likelihood that they belong to the correct class every time, and then a new weight value. So that is our update step. Our maximization step is our update step, okay? And so the probability density function is going to be that function that I talked about up there, right? When it comes to two Gaussians, not a single Gaussian. And so for the fitting process, now that we know these, we can say, well, let's train this for 5 iterations on our data set using the class that we just built. Let's train this thing. So what does training look like? Training looks like we'll take our Gaussian mixture model where we have fitted it to our data set, that we have given our data set to, and we'll say, okay, let's train this thing. So we'll iterate if the current log likelihood is better than the best log likelihood, then set the best log likelihood to the model's log likelihood, and then set the best weight value to the current weight value. Okay, and so we do that for as many iterations as we can, as we define 5 of them. And so once we've done that, notice how our means and our standard deviations and our weight values, that 5th parameter, are all being updated every time. And that is the expectation maximization process. And so once we've done that, then we can look at the mixture. What does it look like? And so this is the end result, right? This is the end result. So we have one distribution to rule them all, Lord of the Rings style. We've got a single distribution. And once we have this distribution, we can then predict, given some new data points, right? Some new spending amount, what is the likelihood, and what is the likelihood that it's going to be a part of a specific class? In our case, it's going to be one of 2 classes. Is this person going to spend or not? And so that's what it looks like. And if we had more features, we could turn this into a clustering problem with circles, which would make it a lot easier to look at. Okay, so what have we learned here? Let's summarize a little bit about what we've learned. Gaussian mixture models take our old friend the Gaussian and add other Gaussians, right? Plural, sometimes. We could have up to as many as we'd like. And this allows us to model more complex data where there are multiple peaks and valleys. And we fit it using the expectation maximization algorithm, the EM algorithm, very popular optimization strategy. And it's a series of steps to find good parameter estimates where there are latent variables. So we initialize the parameter estimates randomly. Given the current parameter estimates, find the minimum log likelihood for Z, which is the data plus the latent variables, the joint probability distribution. And then given the current data, find the better parameter estimates and then repeat that process over and over again. And the distributions that are going to be really bad at first, and slowly they're going to converge and they're going to fit our data set perfectly. Okay? And so this can be used beyond Gaussian mixture models. Instead, think about, well, in this case, you have to guess the number of Gaussians, right? You have to guess, well, I think there's going to be 2 by looking at your data. But what if you didn't have to guess them? Well, in that case, we could use kernel density estimation. But that's for another time. Before we get there, we had to have built the intuition around Gaussian mixture models, a great model if you know the shape of your data more or less intuitively. See you next week. Please subscribe for more programming videos. And for now, I've got to fit my curves. So thanks for watching.